I'm experiencing some technical difficulties. Not me, not the projector, it's my computer. So hopefully it will fix itself in a moment, and there we go. You should get a bigger image so it stares out at you.
It's already staring at me.
There you go. I need to be more intimidating. All right. All right. So I just want to talk. Continue offline. All right. I don't know why it wants to do that. Okay. So thank you. Just a bit of problems with my computer this time. And today's the last lecture on Chapter 6. Tomorrow, we will be continuing and looking at external flows, and you'll get to see some of the stuff from my lab. Actually, I just have to update the slides again. In this part, one of the more important things that we've kind of not talked about yet, and I kind of expanded it a tiny bit before this lecture, is looking at piping networks. So piping networks, we have two different types. The very top one is a pipe in series. The flow rate, of course, is constant because you have Q from one to the next. So Q1, Q2, Q3 are equal. And the head loss is the sum of all of the individual head losses. The difference with pipes in parallel, say, for example, the middle case, A to B, and you have 1, 2, and 3, is that delta P, which is PB minus PA, has to be the same no matter which path you take. So 1, 2, or 3. And we will talk about each of those as separate examples in a moment. Okay, so again, flow rate is constant, head losses are additive. For series, in parallel, head loss is constant, flow rates are additive. And we're going to look at 3 different cases. So you have a 3-pipe system that connects points A and B, and it's in series. And so you're asked to, connecting A to B, you've got water, you've got a pressure drop of 150,000 kilopascals between A and point B, and an elevation drop of 5 meters. And you're given roughness factors. These are relatively smooth pipes. Lengths 100, 150, 80, and diameters 8, 6, and 4. So it's probably reversing flow. And if you calculate the total head loss, it's HA to B, which is PA minus PB all over rho G plus the difference in height, ZA minus ZB. And here, delta H, A to B, will equal 15.3 plus 5, or 20.3 meters. Continuity, V1 D1 squared equals V2 D2 squared, which equals V3 D3 squared. You got rid of the pi, of course, because it's constant in all of these expressions, so you just have to look at the squared term, or pi before, and you canceled it out, so all of them are the same. There's just a ratio
energy is delta H A to B is equal to H major, which we talked about on Wednesday. We did, no, Tuesday. And H minor. So 20.3 equals, yeah, there we go, 2G alpha 1 F1 plus alpha 2 F2 plus alpha 3 F3. And all you're doing there is creating a proportionality constant based on velocities. After convergence, you'll find V1 is equal to 0.565 meters per second. Q1 is equal to pi over 4 d1 squared, which equals 2.84 times 10 to the minus 3 meters cubed per second, or 10.2 cubic meters per hour. Any questions on this?
What are the alpha terms again? Are you just like simplifying like the expression for major loss?
So I know alpha 1, alpha 2, alpha 3, it's just F L1 over D V1 squared, and I can just multiply across. I can get rid of all of the terms in that case. So I shouldn't have written it that way.
So alpha is like the element, like that whole expression.
The whole term plus a proportionality to deal with V1 squared. It's because V1 squared is proportional by, so for, maybe I shouldn't do that way. So if I know V1, I can say V1 is equal to, or V2 is equal to D1 squared over D2 squared times V1. V3 is equal to D1 squared divided by D3 squared times V1. Alpha is just a proportionality, which I should not have used because it was a bit long to try and skip all that step. But you can do that on your own, so there you go. Dealing with problems of pipes in series is something you've done before, so it's not a big deal. You know how to deal with them because you've looked at them. You know that you have continuity, conservation of mass throughout their conservation of volume flow when it's incompressible. These are more difficult, and they're more difficult because they're conceptually more difficult. So the only thing that you really worry about is that the head loss, H1, H2, H3, in all of these cases, assume the same three pipes are now arranged in parallel with the same total head loss, delta H to A to B, 20.3 meters. Compute total flow rate that we calculated 20.3 in the previous part. Q total equals Q1 plus Q2 plus Q3. Oops, sorry. Solving for those each independently, Q1 equals 62.5 meters cubed per hour. Q2 equals 25.9 meters cubed per hour. And Q3 equals 11.4 meters cubed per hour. And Q is equal to Q1 plus Q2 plus Q3, which is equal to 99.8 meters cubed per hour. So we went from 10 to 100 by just maintaining the same pressure drop across there. And again, I've skipped a lot of steps here, and I do understand that. But basically, again, something that you can do on your own. You've got weekends, nothing better that you can do. But all this is using the head loss, and again, using the same information you had in the previous problem to solve through for all of them.
Finally, a 3 reservoir problem. Same 3 pipes now connect 3 reservoirs at different elevations, 1, 2, and 3. And you have Z1 equals 20 meters, Z2 equals 100 meters, Z3 equals 40 meters. Continuity has to hold. Q1 equals Q2, or Q equals Q1 plus Q2 plus Q3. Flow towards a junction is positive, away is negative. Head loss in each pipe is driven by the difference between reservoir height and junction head. So the junction is here, where that point is. So So if we start out with just a guess that the junction is at 40 meters, we end up with a negative flow from the system. And if we continue and lower that junction height to 30 meters, we get a positive flow. And the only thing that that tells you as you're doing your iterations is that that is going to be the range of possible solutions. So the solution is somewhere between 30 and 40. It's not linear, it's a kind of more iterations to sort of go through. But if you linearly, well, you can start out by linearly interpolating pipe 1. If you do an interpolation and then sort of solve through for things, you'll find that pipe 1, which is below the junction, has a negative flow rate, minus 14. No, that's not what I wanted. Pipe 1 is minus 52.4 meters cubed per hour. And the other two balance it out. So 47.16 and 52.4, and you end up with a slight offset from 0.7. And within the percentage accuracy we can achieve, that's actually pretty good. If you want to be better
Then you would do another iteration around 34.35, or sorry, yeah, 34.3, and then start adjusting a little bit up and down, and you'll see how much it changes. But you're going to get to the point where you're calculating to the 100th and 1000th place, and if you're dealing with reservoirs of water, it doesn't make a lot of sense. The main thing that I want to sort of highlight here, and this is why I sort of added these examples, and I do encourage you on your own to try them out, is just the basic rules. Net flow into any junction must be 0. Q in minus Q out is 0. The net pressure change around any closed loop must be 0. And the hydraulic grade line at a junction has only one elevation. So if you go to a junction point, it's always going to have the same elevation no matter which path you took into that junction. And a junction is just where all of the pipes come together. Friction coefficients, all pressure changes have to satisfy the Moody diagram, and minor loss friction coefficients. So you have major losses, minor losses, and you know what? I might, for my own happiness, look up the Hardy-Cross method and see if I can get a copy of the paper, because I might. But it's really, again, very clever method. It's not the way you do this. Most modern approaches tend to use software, and here you go. This is not something that you might use some of it, but EPANet, it's free and open source, but there's a whole bunch of others, WaterGems, WaterCat, Hammer, Info Water Pro, Mike Plus, Synergy Water, and Fathom and Arrow. And that industrial, the last one is probably the one you might use. What's interesting is that there is a lot of open source software out there, and again, my experience, and I'll sort of throw some comments towards the end of this lecture about open source, but I think open source is really, really good, and it's pretty valuable to learn some of this, because if something goes away, so commercial software comes and goes, open source software has survived pretty well, especially if it has already had a long life. So a lot of these have been pretty good. Series systems, high resistance, flows equal head add, low resistance in parallel, so higher capacity, and that's why you do that. Heads equal flows that add together, and networks and junctions you solve by iterating on junction head or mass energy balances in loop, which is the Hardy-Cross method. And that's just the same thing. So this is a more detailed example that I have done. And I just wanted to start with that one. So I have three reservoirs, one, A, B, and C, and within it I also have pipes 1, 2, and 3. I have a junction where that dot is, and I have converted, again, I've converted all of this to SI units, and generally I don't solve problems on my own in English units because I mess up the units. Right, there you go. And I can't remember the gravity constant and all the rest of them for slugs and pound masses and pound force. Lengths are okay. But the heights are 30.48 meters, 6.096 meters, and 0 meters. So this is the bottom, this is a midpoint, and that's the top. Diameters are all the same, 0.31 meter, and lengths are 304.8, 152.4, 121.9, and the friction factors is given to you, and they're all the same. Minor losses are negligible in this case, so you're just focused in on major losses. Find the flow direction in each pipe and the flow rates into each reservoir. I probably am not going to do what I say here. I'm just, yeah, I am. It's out of A, out of B, and towards C. Everything is moving. So it's going to, if you looked at the original, or remember the original diagram, A is at the very top, B is some midpoint, and C is at the very bottom. Right continuity at the node, and energy, head equations, solve if no real positive, reverse the guess directions and repeat, and for the initial, which is going to end up being wrong, the governing equations admit no physical solution. So we adopt the physically correct solution, which is going to be out of A into B and C. Now that's not how I would start this problem. I'm sort of jumping ahead in terms of the iteration. Normally I would just say, hey, it's all going to come out here, it's going to come out here, and it's all going to end up in here. But the reality is that it comes into both. But in order to make my life a little bit easier, I'm going to start with that and say that Q1 equals Q2 plus Q3. And if I do that, then I can also say V1, A1, now I'm going to do pi over 4 d squared equals V2 pi over 4 d squared plus V3 pi over 4 d squared. D is not changing in this particular example, and I can cancel it out, so I get V1 equals V2 plus V3, and then I write my energy equation between all the points. And if I do that, Z A minus ZB F1 L1 over D1 V1 squared over 2G F2 L2 D2 V2 squared over 2G Z A minus ZC F1 L1 D1 B over 2G. Okay. So with that, I have this term right here, which is 20. This term, which is 10. This one, which is 8. I have 24.39 meters and 30.5 meters. And G is 9.81. All right, so all that's covered, and that's all of the terms that I have to deal with. So if I do that, I solve the system, and I end up with V1, which is approximately 0.878 meters per second, V2, which equals 4.81 or 5 meters per second, V3, which is 3.96 meters per second, Q1, which equals 0.064 meters cubed per second, or sorry, Q2, oh, this is wrong. For some reason, I didn't want to do this in the right order. So V2 is 0.78, V1 is 4.85, Q1 is equal to 0.354 meters cubed per second, and Q3 is equal to 0.289 meters cubed per second. All right, so you have all of the areas, you have all of the information, and the English unit result, just for comparison, Q1 equals
12.5 feet cubed per second. Q2, 2.26 feet cubed per second. And Q3, which equals something else, 10.2 feet cubed per second. So that's just for if you have a desire to solve it in English units, those are the numbers you would get. Having solved all of that, you end up with 30.4 meters out of this, 24.35 meters, and so the height difference, based on sort of using the result that you got, actually works. It's correct. And so good agreement. There's a rounding error associated with sort of calculating things, but there's always going to be a rounding error. You could do this problem again, and you'll get a slightly different result. And that is if you use, again, Holland's equation, you guess the directions, and we would end up guessing directions exactly the same way. Guess out of A into B into C, compute them, get Fi, use epsilon over D as appropriate, enforce the energy equation, and keep Q1 equal to Q2 plus Q3. Iterate until the head balances and everything is correct. If you do that, you'll get Reynolds number 1 of 1.48 times 10 to the 6th. Reynolds number 2, which is 2.68 times 10 to the 5th. Reynolds number 3, which is equal to 1.21 times 10 to the 6th. This is going to be, you would then use that, you can check against Holland, and you will end up with F1 is 0.011, F2 of 0.015, and F3 of 0.011, which is roughly the numbers they gave you in the problem. In fact, the problem probably would be better if they used 0.01 instead of 0.02. And it also makes sense. These are highly turbulent flows. They're on the order of millions. And again, I'm not a big fan of the Moody diagram, but if you look at the Moody diagram at about 1 million, it's going to be low. It won't be 0.02. So you'll get slightly different results. 3, 5, 4. Well, about the same, actually. Actually, you get the same. 0.064. Q3, 0.289 meters cubed per second. Again, when you're solving these problems and looking at how things are going, it's often better, and again, strongly recommended. When I created all these notes, I created them using Holland. There is absolutely no benefit of using Holland versus Swami Jain. There's a big benefit by not using the Moody diagram. So certainly, it's up to you how you do them, but just a reminder that you have a choice in how you approach them. So we're starting to touch on things that, for example, I do in my own lab, but one of the things that really comes out is the Moody chart is an excellent correlation, but it's only reliable for ducts of constant cross-section. So if I start to vary the duct size a lot, then it's not going to be easy, or I need to do a lot of iterations to get the solution to work. As soon as the cross-section varies, the diffuser, nozzle, or round an obstacle, we have to rely on experimentation. So in terms of where we are in chapter 6, this last one right here is where we've been. But in chapter 7, we're going to talk more about the first two, vortex shedding from a cylinder, drag on spheres, actually, and then secondary flows we also covered in chapter 6. Flows over a dam spillway is something that you will sort of hear about from your colleagues, mostly in civil, except when you have to do a The loss coefficient data presented so far is for turbulent flow. Laminar losses are proportional to V, not V squared, so it's not FL over D, V squared over 2G. Instead, it's going to be delta P, V over mu V. And these losses can be substantial and comparable to the main Poiseuille friction loss, especially in micro and nanofluidic flows. So if you look at a lot of the, have you ever seen microfluidics? Did Professor Gunther show you any of his work on that? Oh, okay. All right. All right, microfluidics is just very small channels on the order of microns, and where you introduce all sorts of weird sort of bends and things like that. And that's where pressure drop gets really important. And I have re-shown the same slide. Oop. And where it's sort of relevant to chapter 6 and sort of allows me to close this out, you have diffusers with constant is a duct section with constant or increasing area designed to reduce fluid velocity, recover pressure head. And so you have two designs. There's one which is a flat surface, essentially linear expansion, and then another one which is more expensive to make because it takes a lot more skill in terms of technician time, which is a curved surface. So you can have flat walled, and you'll get different sorts of results dependent on the angle. I think this particular chart is for the flat wall case, and you have L over length over width as the entry point, and you can see that you get CP max. So what is CP? Oh, okay. Just a reminder, on the second one, up until recently, for me, maybe not for you, 1950 is sort of when we started to shift over from sort of experience-based and towards more model. And experiments and things like that sort of help. Pressure recovery coefficient, C sub P, is equal to the exit minus the throat over the ideal pressure rise that you want to achieve. Ideally, you want a number to be as large as possible and as close as possible to 1. It's hard to achieve. And if you have frictionless flow, and we often kind of assume that with relatively smooth ducts, and that's kind of reasonable, you can do things so that the velocity of the exit over the velocity of the throat squared is the proportionality. And if that's the case, you know that Q1 equals Q2, and you can do Q over AE divided by Q over A throat, and if you do that, you end up with an aspect ratio. So for an aspect ratio of 5, you end up with a pressure recovery coefficient of 96%. But the reality is that you're not going to achieve that. You're not even going to come close. So 24% is probably more reasonable. And the main reason for this is something we've talked about in the last lecture in a little bit more detail, where you have flow separation. So you have a flow that comes out, and ideally it will behave like it does on the top. It spreads out nicely, and it comes to the very top of that, and it will proceed and move gently out. The reality is that in most cases, high momentum fluid will sort of continue. It will cause a secondary flow, and there's a stalled flow that occurs, and that reversing causes a pressure drop. And that's part associated with a adverse pressure gradient where delta P over X, where X is the downstream distance, is greater than 0. And that kind of makes sense. You should sort of say, hey, it's Bernoulli equation here, high speed going into low speed, and if that's the case, then pressure has to increase at the same time. Gradients slow the fluid near the wall, causing viscous boundary layer to detach or stall. Separation leads to backflow, turbulent eddies, and reduction in pressure recovery. Okay, so ideally you have no stall.
you mostly have transitory or bistable stall, and you try to avoid jet flow. So again, it's really dependent on the inlet momentum of the fluid. If it can just sort of power its way through, it will cause all sorts of secondary flow. If it can sort of expand gently without a lot of trouble, it will have no stall. But all of these cases sort of end up as different values on that chart I showed earlier. Diffuser performance, and again, I'll remind you that in all of my references to tables, charts, or whatever, these are to the previous edition of the text. Area ratio, divergence, angle, slenderness are geometry that are important. Inlet flow and inlet Mach number. Inlet Mach number, not so much. When you're dealing with duct flow, you're not dealing with something that is going to be that difficult. So there we go. Here's a plot. L over the inlet, aspect ratio, and you see different values of C sub P. So if any of you are considering, for example, going into a PEY next year, you will see lots of charts like this. Charts for different sorts of things. You'll deal with pumps, you'll deal with turbines, you'll deal with duct design, and you will be expected at some point to read charts that look like this and sort of say, hey, which design? And often what your limiting factor is not just, hey, I want to hit that high C sub P of 0.7. It's also how much room do I have for my diffuser to fit into the spot. And so the design considerations change how you approach all of this. There's always an ideal solution, but there's also the practical solution of what your client actually needs. So if you move forward from there, you have something that I've spent a great deal of time on. Velocity, you can measure flows, and you can do that with local properties, velocity, pressure, temperature at a point, integrated mass or volume rate through the duct. And the final section deals with local velocity and volume flow rate. So here you go. So within my lab, since I can do self-promotion, well, not so much here. That one. Within my lab, I use the last 4 items. Actually, yeah, I use the last 4. I collaborate with people, so anemometers, wind or airflow anemometers, A, B, C, and D to a certain extent. D, I think, is a volumetric flow one that you put into a pipe. All of those are designed to measure local wind speed. So if you're doing something in the field, often it's useful. So for example, I've got a project with Environment Canada. We're looking at precipitation gauges, and as part of that, they measure the wind speed at the precipitation gauge. And the precipitation gauge, so to kind of fill that in, is a gauge which measures snowfall. And so there are a whole bunch of sites around the world where they measure snowfall, rainfall, and what they try and do is relate that to climate. So all of our climate models are going to be based on a decent set of measurements. And so the first 4 approaches are important. Within the wind tunnel, I use hot wire. I have a collaborator up at Utias who uses hot film. Both of those are local measurements, and essentially you put a hot cylinder, which is 5 microns in diameter, into a flow, and you cool it. And the response of that wire or the film tells you what exactly the velocity is. The next one is pitot tubes. They don't measure velocity, they measure pressure, but you can convert through Bernoulli into velocity. The other 2 methods, and I kind of threw that one up there, is PIV, particle image velocimetry, which we've been working on for a number of years, and LDV, which I used back in 2000, and it was great, except to put things in perspective. Hot wire cost me roughly $5,000 to set up, and I can do all of my own software for that, so it's really good. Pitot tube's easy. PIV, we do our own software. Setup cost is about $100,000.
that to measure flow over airfoils and do things like that. LDV, where you measure at a single point. These are single point measurements. This is a planar measurement, so you measure an entire field at the same time. I probably should throw in a picture from one of those. But here you're doing a single point, and to get one that actually works properly is about 500,000. So that's why I don't have one. First one is the pedostatic tube. So you'll notice that you measure both stagnation pressure and the free stream pressure. And you have the free stream pressure measured around the periphery of the pedo tube a little bit downstream. And you have 4 to 8 holes typically. And it's really good for measuring mean flow in non-disturbed flows. And so to a large extent we use that in a wind tunnel and use that to calibrate what we're measuring. But if you are off of the flow direction, off of the wind direction, you will have an error associated with it that makes it very difficult to use. The nice thing about it is that this is a practical application of the Bernoulli equation. And in fact, if you look at probably some of the earliest applications, it's probably into the 1800s that they were using pedo tubes. It's really good because you can do simple things with it. You just measure it with a manometer, and you get the height difference, and you get from that directly what the velocity is. Sensitive to yaw angle, not suitable for very low velocities. Although they did have angled manometers that were really cool, but nobody wants to use those anymore. Hot wire, really easy to program within LabVIEW or any other code. Setting it up is straightforward. It also has very high time response, and one of the big difficulties I have, in fact yesterday we were talking in the turbulence course, which I teach at the graduate level, about these types of devices. You have a fine wire in a flow and you heat it, and you heat it slightly above the ambient temperature. And if you have a turbulent flow, you have a fluctuation, and so that fluctuation is going to be associated with changes in velocity. So I can measure the fine scale change in velocity with something like this at about 5 kilohertz, 5 to 20. Hot film anemometer, not so good. They don't respond by maybe about 1 kilohertz. They're thicker, they're slower, but they work really well in liquids, and my colleague up at UTIAS, Professor Ekmeshi, is the one who uses that. We've used, or I've used LDV in the past, mainly for very complex environments. So the last time I used it, and the student who did it had to essentially take an existing LDV system, rewrite all the software back then in 2000, no Python, and did measurements in a cylinder, an engine cylinder. So we had a particular type of cylinder we developed. This is a very complex flow to do things in, but it was a remarkably good set of measurements that he did. A really simple way of saying or dealing with LDV is you have 2 beams that intersect with each other. That causes a light interference, so you have bright, dark sort of fringes that appear. And as a particle passes through that, that reflection can be measured. And essentially you can use a stopwatch. It's not really a stopwatch, but it's a stopwatch to sort of measure that off. In industry, they're not interested in that. They want to know what the volumetric flow rate is, and you can use different types of devices. So for example, in the lab, you've done cases where you've used volume weighing tanks and measured how much flow you got over a certain amount of time, and then calculated it from there. You can also, and you did this on the midterm, use various types of mechanisms to calculate pressure drops, and an orifice plate is a good example of that. Venturi meters flow nozzles, and you can find all sorts of details about them in other sources. Oh, all right, I gave you the full solution to this, so I don't feel bad about rushing through it in 6 minutes. Same sort of thing. I have 3 lines, H1, H2, which are at 0.305 meters, and H4, which is at diameters for all of the lines, 50.8 millimeters. And again, at this point, I think you're used to this where I do convert from English to SI. This is why you get these odd numbers. You have Ka for minor loss coefficients, Kb 5.6, Kc, which is 5 for the angle. So you're given all of this information, neglect friction, and the three lines meet at a junction, into the junction, and they come out C out of the junction. So you have flow in, flow out. All pipes have the same diameter, so you can use the same area, and as usual, gravity is 9.8 meters per second squared. So QA plus QB equals QC. Okay. You can then create a summation, and the summation on the minor losses is just going to be 1 over 2G areas, the cross-sectional area squared, Ki times Qi of each of the individual terms. And in that case, I can create a constant C sub Si, and I have a number of 1.24 times 10 to the 4th meters to the minus 5 seconds squared. And again, when you're doing these calculations, it's often really useful to keep your units so you remember or check to see things are actually going to work out. So Ka was given, Kb, Kc were all given for this particular problem. Equal piezometer heights at points 1 and 2, and K Qa squared equals Kb Qb squared. Drop from 2 to 4 is 3.305 meters, and you put CSI and you satisfy everything and calculate what the total head loss is in the system. So you have 3 equations and 3 unknowns. You can solve through for everything and iterate, iterate, and iterate, linearize. Okay, anyways. This is more complex than I wanted to write it out, but it's useful to sort of show you. You end up with a solution that is Qa, which is 8.2 times 10 to the minus 4 meters cubed per second. Qb, which is 1.0 or 1.1 times 10 to the minus 3 meters cubed per second. And Qc, which is 1.9 10 to the minus 3 meters cubed per second. And you can keep iterating once more. And of course, I cut that off. I'll have to figure out what that number is. But it's, you know, it's not changed too much in that particular case. So it's going to be about 2, and head drop there. God, I don't know why I did that. Okay. So area, all that, all the terms are there. Okay. And so this is a good place to stop for this. You have a head loss for all of the terms. The only reason I did this particular problem is that this is a piping network problem, and it has minor losses. The first one I did not have any minor losses, and I think it's kind of useful to at least introduce you to something where you use both. And so that's why this one is there. It is a full solution. If something's missing, please tell me. But any questions? All right, I will see you tomorrow.
We have an assignment due on Sunday for chapter 7, but we haven't covered chapter 7. Is there any way you could delay it a week?
Yeah, I didn't realize that.
That's okay. It's just like, yeah, we can't do it. Like as of right now, with our
It's
knowledge.
good character building. No, I'll figure out how to adjust it.
Okay, thank you so much.
Yeah. Yeah, because next week is still, so I can do it the next Sunday. I can't do it after that.
Oh yeah, that's fine. Next Sunday.
So Friday, I will start chapter 7.
Yes.
Yeah.
Thank you.
Yeah, thank you.